Well, so welcome again on the road towards developmental artificial intelligence. The outline today will be about organization of behavior in time and space. So far, we have mostly spoken about organization of behavior in time, but as I introduced last week, if we want to implement more sophisticated agents that interact with the real world, it is not only about learning regularities in time, but also regularities in space. So I will introduce our new formalism for spatial-temporal coupling to describe a coupling between the agent and the environment that has spatial regularities. And this will lead us to a new cognitive architecture, and I will show a few demonstrations. Then we'll continue our exercise of implementing self-programming agents. So again, a reminder of the theoretical ideas. So it's still about learning, that is discovering, organizing, and exploiting regularities of interactions in time and space to satisfy innate criteria, so develop a form of self-motivation. Here I have slightly rephrased our objectives. Previously I was saying that we want to program our agents without ontological assumptions about the environment, and now I insist on the fact that we want the agent to autonomously construct an ontology of reality. That is, we want the agent to discover by itself what categories of entities exist in the world and begin to construct its own knowledge about the world based on the interactions that the entities afford. I introduce a new concept, which you may not know, the concept of affordances. And I will explain that in the next slides. So I remind you that it's about learning sequences of interactions and abstract episodes of interest in a hierarchical manner. So with short episodes that are sub-episodes of longer episodes, in such a way that at a certain level of abstraction, it matches sequences that were previously learned, which propose subsequent behavior, and then select the proposed behavior and re-execute it. This is this which provides the self-programming effect. So the decisional process of the agent is rising up one level of abstraction so that the decision concerns a higher level of behavior. So this mechanism of abstraction of behavior is a very fundamental aspect of cognition. So for example, when you learn to ride a bicycle, you automatize the behavior of controlling the bicycle, and then you do it automatically. And it's not only a problem of repeating sequences of actions. For example, if we implement a robot that just records its behavior and re-executes exactly the same behavior, this behavior will not be adapted to the new situation. So it's not about repeating exact behavior, but automatization of the control of interaction. At a higher level, language involves also a form of self-programming. So when you meet somebody and you want to say good morning, you do not control all the the behavior of your mouth and your tongue to pronounce these words. You just decide to generate this behavior, and then it is generated automatically. So the highest you climb up in the abstraction of behavior, the highest the more you develop more complex goals. And this is done without any predefined goals. So this was purely sequential learning, and I showed that it already allowed to implement a agent that organized its behavior in space with this experiment. Just by learning sequences of interactions, we could generate behaviors in space. So for this agent, its world is a purely sequential world, but when we observe it from the outside, we see organization of behavior in space. The agent ignores that it is in space. Now the problem is how to go beyond these behaviors. So in this example that I showed you before, those two gray sharks implement this sequence learning mechanism, but there is an additional mechanism that decide which object of interest will be its focus of attention. So you see the color of its eyes here, this blue cyan color means that it can focus on this blue cyan flower, and once it has chosen an object, it purely enacts its sequential learning mechanism. But then when it reaches an object, then it triggers another interaction. So typically, if it reaches a wall, it will bump the wall. If it reaches a fish, it will eat the fish. And if it reaches another agent, it will cuddle with the other agent and trigger the behavior of cuddling. So it will associate the various interactions that are afforded by the various objects, and it will associate these interactions on the basis of spatial overlap, because it will notice that those interactions are afforded by a particular place in space. So, for example, the interaction to eat fish is positive, and the interaction to bump walls is negative. So after a while, it will learn to avoid walls and to seek fishes. So there is this second level of learning, which detects overlaps of interaction in space in order to find out that some entities afford categories of interactions in space.
Oui, alors voilà, c'est-à-dire que en fait, il a toujours pas de
So to do that, it does not construct a map of the environment. It is not performing a pathfinding algorithm or solving a maze. It only uses a local egocentric spatial memory to detect spatial overlaps of interactions, so as to detect that what is seen as a wall is also felt as a wall. What is seen as a fish is also felt as a fish and affords the interaction it. And besides that, it's only learn sequences of interaction to reach specific categories of objects. So it's the same sequential learning algorithm, but this algorithm focuses on different objects of interest based on the interactions that are afforded by these objects.
Donc c'est purement un apprentissage de séquence. Le seul truc, c'est que là, c'est plus compliqué parce qu'il peut voir plusieurs choses à la fois, tandis que dans l'autre exemple...
Difficulty here is that it can see several things at the same time, so it has to choose one object on which to focus and to organize its behavior sequentially on the basis of interacting with this specific chosen object. So here it's the other agent. And then when it sees the fish, it decides to interact with the fish, so move towards the fish. Because it knows that the fish affords the interaction eat, and eating is positive. And here it knows that the other agent affords the interaction cuddles, and cuddling is also positive. So the only additional mechanism is the mechanism that allows it to choose amongst the different objects that it can see in its visual field, the one that is the most interesting because it affords the most positive interactions. So as a result, it can explore the environment because it is attracted by silent objects, but it has no map of the environment, so it is not there's no algorithm that makes him explore the environment as a maze, if you will, as a maze to solve.
Il lui faudra une mémoire spatiale. Donc je vais y arriver à cette mémoire spatiale. Alors je vais approfondir un peu ce concept d'affordance.
So let me talk a little bit more about the concept of affordance. So an affordance is a property of an object or an environment that allows an individual to perform an action. It's the idea that when we see or perceive an object, it invites us to enact a specific action. So a typical example is a door handle that suggests us to open the door. So when we recognize a possibility of action on an object, it invites us to enact this action. So it's a useful concept to us because it's situated at the coupling between the agent and the environment. And it corresponds to psychological theories that explain us that we see the world in terms of possibilities of interaction. And we have a tendency to answer to these possibilities of interactions that we detect in the environment. So, for example, there are neuro disease that makes the patient unable to control their behavior, and they cannot refrain themselves from answering to an affordance. So they see a possibility of action in the environment, and if we don't have those higher level mechanisms that allows us to choose between the different possibilities, if those mechanisms are impaired, then the people may not be able to resist the possibilities of interactions that are afforded by the environment. So this relates to this mechanism of self-programming or automatization, because we have this natural tendency to automatically answer to possibilities of interactions. So, for example, you can experience this when you are hungry and when you see appetizing food, then you cannot refrain yourself from eating this food. So you can't help responding to the affordance of eating. So the concept of affordance captures this phenomenon that is that relates to the coupling between the agent and the environment. It's at the same time a property of the object, but also a property that is interesting and important for a particular agent. So it's both related to the object and to the subject. So that's why this notion of affordance is useful to us to think and design our affordances. And of course, it's related to what I introduced in my first lesson, that we never know the world as such, but we only know the possibilities of interactions that are afforded by the world. So what we are going to try to do is to implement agents that detect affordances and that categorize the environment with regard with the affordances that they have. So to that, I will go a little bit further beyond the formalism that I introduced last week. So I remind you the traditional formalization, the environment sends an observation to the agent and the agent chooses an action. And I told you that, so in our exercise, we begin with the agent chooses an experience that it experiments in the environment, and the agent receives a result of this experiment. This is what allows us to think in terms of interaction. So an interaction is the coupling between an experience and a result. And because we can think in terms of interaction, we can design this self-programming effect because of the hierarchical organization of interactions that I introduced last week. So we can say that two following interactions can be abstracted as one composite interactions, and you cannot do that if you separate observations and action. And then eventually we simplify our formalism by totally removing the notion of experience and result and only keeping the notion of interaction. So instead of saying I want to do an experience and obtain a result, we totally collapse the experience and the result, which is totally logical at the psychological level. So if you, for example, if you feel something through touch, if you don't move, you don't feel. So moving and feeling are undissociable. So an interaction, for example, would be to move and to touch, to feel something at the same time. And the agent will choose the interaction. I want to touch something, but the result will depend on the environment. So if there is something to touch, then the agent receives the same intended interaction as an actually enacted interaction, the interaction touching, moving, and feeling something. And if there is nothing in the environment, the agent receives another interaction which corresponds to moving and feeling nothing. So I introduced this formalism, which I called radical interactionism, which allowed this recursive sequence learning. So the example of touch and feel is perfect because we see well that they are undissociated. But it works the same with vision, as I showed in the previous example. You have the feeling that you see the world through visual data that enters your eyes, but in fact this is a form of illusion. You in fact construct a representation of the world through scanning the world by moving your eyes.
Comme je disais, le fait de raisonner sur les interactions nous permet de construire un ensemble plus élaboré d'interactions composites. Donc on va mettre l'ensemble des interactions, si vous voulez, va augmenter avec le temps.
So the fact of thinking in terms of interaction allows us to construct to learn to dynamically learn new interactions and develop the interactional domain.
Mais dans le TP, on ne va pas aller jusque-là en fait. Dans le TP, on raisonne comme ça.
So in the exercise we think like this with the experience and result. But here I introduce the formalism, radical interactionism, just to explain how we can go beyond that.
Alors en fait, on va aller un peu plus loin. Un autre problème, c'est de dire, ok, les régularités dans le couplage entre l'agent et l'environnement, c'est pas seulement des régularités dans le temps, c'est aussi des régularités dans l'espace. C'est-à-dire qu'il peut exister des objets qui occupent l'espace et qui sont persistants, et ça va être extrêmement difficile de s'en rendre compte.
Our problem is for the agents to find out that there are persistent entities in space and not only sequential regularities. And we found that it was very difficult for an agent that is only sensible to sequential regularities to discover the existence of persistent entities in space. So to address this problem, we will provide the agent with additional information. So in addition to the intended interaction and the enacted interaction as I introduced previously, we will provide two additional information. So spatial information called sigma here. So we will simulate the capacity of the agent to perceive where is situated spatially its interaction. So for example, as humans, when we interact with the world, we are usually able to situate in space the origin of the interactions. So when you hear a sound, you usually approximately know where it comes from, and when you see something you can see where it is, and when you touch something you are able to localize it in space, and you infer this information from various data. So for example, your auditory system uses interoral phase difference, and your tactile system uses your body schema, and your visual system uses eye convergence.
Pour la vision, vous utilisez la convergence oculaire qui vous donne une idée de... Comme si c'était l'agent.
So this information is egocentric. So it's a spatial position within the agent's own referential. However, we are a bit cheating because we give the coordinate of the origin of the interaction in an egocentric referential. We give it approximately, but we give it as a metric measure instead of providing an information from which the agent would have to infer the position of the origin of the interaction. And the second information that we provide the agent with is what we call the spatial transformation. So it's the spatial movement induced by the enacted interaction. So it simulates the vestibular system. It's designed to provide the same kind of information that our vestibular system provides us. For example, you can experiment to sit on a wheelchair, and if somebody moves the chair, and if your eyes are closed, you are perfectly able to localize objects in the room, even though you cannot see the room, but you are just aware of your own displacement in space. So you have this sense that informs you about your own displacement in space, which of course helps you a lot to organize your behavior in space. So we'll provide the agent with this information as if it had this sense. So we'll see what we can do with that. So if I use the example, if I go back to the example of the agent that is in the small loop, and it can touch walls in front, to the left, and to the right. So for example, when it shows I want to touch in front of me, but it has no idea what this interaction means. For example, if there is a wall in front of it, we return the enacted interaction touch a wall, but additionally we return the spatial position. So if it touches in front, the spatial position is 1, 0, and touching involves no movement, so the spatial transformation is 0, 0. So if it moves forward, the spatial information will be a translation of the world backwards, because we give the displacement of the world relatively to the agent. And when it turns, it's a rotation of pi over 2 to the left or to the right. So the agent still doesn't know to what the interactions correspond, but it knows their position and it knows its displacement. So it can keep track of the spatial position of interactions and discover that certain they may overlap in space, and so they can associate interactions that overlap. And from that, it can discover that in this environment, there are two kinds of phenomena, if you will, the phenomena empty cell and the phenomena wall, that each affords different possibilities of interactions. So as before, it starts with randomly picking interactions, but on the right here you see its spatial memory that allows it to place interactions in space and detect spatial overlaps, so it can associate the various interactions afforded by the various phenomena, and so it can faster than before learn to organize its behavior in this loop, because it detects that there are two categories of objects in its environment, empty cells on the wall, even though it does not construct a map of the environment. As you can see, the spatial memory of the agent is only short term, and the interaction disappears after on the short term from their memory. So it does not construct a map, it just detects categories of objects based on spatial overlaps of interaction. So here in the sequential trace, we see on each step the map that it constructs in the square surrounding it. So of course, this helps the agent a lot, and it learns much faster than with the sequential learning algorithm only. So in this case, to implement this, we implement this cognitive architecture. So it's still based on sequences of interaction, and we still have this hierarchical sequential memory as before that learns hierarchies of episodes. But in addition, it has a spatial memory centered on itself in which it can place interactions and notice overlaps of interactions. So notice that there are categories of objects that consistently offer the same interactions. And it can categorize those objects to construct an ontology of the different categories of objects. For example, this one always offers bumping and feels like touching hard. So it can begin categorizing objects according to the interactions they afford. So then when it enacts an interaction such as touching in front, this will evoke the other interactions that are afforded by this category of objects. So here is the example with visual interactions. So it has the same kinds of interaction, but it can detect their position in space and place those interactions in spatial memory and update its spatial memory as it moves. So it can notice that some interactions overlap and are afforded by the same object. So it's a little bit like before with the sequential mechanism only. It has learned the staircase behavior. And the fact that it situates interactions in spatial memory allows it to deal with the presence of several different objects in space, which it could not do with the sequential system only. And also it can learn to interact with different categories of objects. Here it discovers that these walls afford bumping. And here, because it noticed that the other object is edible and this object is bumpable, so this allows it to choose among different objects of interest with whom to interact. So it's a little bit like an insect that is attracted towards the light and cannot help going toward this light, even though it bumps into it. But then it sees this other object. So here again we introduced a wall between the agent and the edible target, and what we would like to do is implement agents that realize by themselves that they should bypass the wall, but it's still an object of study. So in our current version of our algorithms, it's not smart enough to bypass the wall. As I said, it's not only a problem of pathfinding, but it's a problem of realizing that there is another object in between a desirable target that can explain that it doesn't see the target anymore.
Comme il sait pas la distance, si on le laisse très longtemps, il va s'en désintéresser. Mais statistiquement, quand il y a un objet vide,
the reason why it keeps bumping into the wall is that he believes that it can move forward, and moving forward toward a target is positive, so it tries to move forward even though it bumps into it.
Oui, alors, voilà, c'est-à-dire que, sauf qu'on veut pas faire ça, on veut pas construire une carte, en fait, parce que...
So we don't want to have a precise spatial memory to construct a map, because because we don't want to consider that they are precisely placed, because it's impossible to place interaction precisely if we want to implement this in a robot, for example. So if we wanted a robot to construct a map of its environment like this, it would not be precise enough to be exploitable. So we only use spatial memory on the short term because we assume that on the long term it will be false anyway. It will not be precise enough anyway. But on the short time, it's useful to detect spatial overlap of interactions that are afforded by a single object. And we cannot assume that objects are necessarily persistent. Some objects can disappear, they can be eaten by another agent, or they can move by themselves, and so on. So we cannot assume that objects are always persistent, but we expect the agent to learn when they are persistent. So we take inspiration from neuroscience. This is a human brain, and we know that there is an egocentric spatial memory on the short term in the superior colliculus. So, for example, you can make experiments, for example, with animals. If you see that an object edible is present in the surrounding of the animal, you will see an activation in its superior colliculus. Or if it focuses its attention on a particular direction in space, it will activate its superior colliculus. So we know that there are areas or volume in the brain that maintain this correspondence with the surrounding space, at least approximately, and at least the direction, if not the distance. So currently we implement this mechanism of spatial memory, but there are many other forms of spatial referential in the brain. There are halocentric referentials, but we move progressively. We start with only the egocentric referential. So there is the hippocampus, for example, that constructs an allocentric referential to help me organize my behavior, for example, in this room or with objects on this table and so on. So there are many different referentials or possibilities of representing space in the human brain, and we begin with this egocentric spatial memory. So this implemented the where on this figure. The interactions implement the how, which interactions are afforded by specific objects. And we also implement a little bit the what, because we send the color, the visual color of an object that the agent can see, which allows recognizing the object that the agent sees.
Énormément de choses en plus à implémenter. Dès qu'on rentre dans le détail, c'est un plan un peu plus détaillé.
But of course, it's only the beginning. If we enter the details of the brain, there is much more to that. Here is a more detailed map, and so it's only the beginning, and we have much to do.
Ouais, c'était ce que je voulais vous montrer. Alors ça pose plein de
So it raises many issues. It's mostly an ongoing research, and we don't know exactly how to proceed. So one problem that arises is that if we add this additional information, the spatial position and the spatial transformation, we lose the possibility of recursivity that I introduced earlier. So last time I told you that we could construct composite interactions, and the agent would ignore the primitive interactions and would see the world in terms of composite interactions. And this allowed us to design this algorithm that could learn recursively. But if we add the informations of position and transformation, we don't know how to reconstruct this information at the higher level. So we don't know how to maintain this recursivity across levels of interactions. So the spatial transformation could be a composition of the spatial transformation of each primitive interactions. So we have solutions, but we are still exploring all the details.
Positionné à tel endroit, mais qu'il apprend une autre interaction qui est peut-être positionnée avec un autre.
Especially to associate the position of each primitive interactions and follow up with the displacement. It's very difficult to synthesize this information at a higher level.
On y arrive un peu, on fait des compositions et puis on sélectionne que les interactions qui conservent toujours le même objet, donc avec des petites règles, on s'en sort, c'est ce qui nous a permis de faire les expérimentations que je vous ai montrées. Mais au niveau théorique, comment
so we managed to deal with that, and that's what allows us to implement the demonstrations that I showed you, but it's not the whole story.
Alors, le fait d'avoir cette architecture là, où on a un peu deux différents modules, on va pouvoir les faire réfléchir entre eux, enfin travailler entre eux.
So with this architecture here that has several modules, so the sequential module and the spatial module, it allows us to study how those modules can interact and to implement simulations of sequences of interaction in spatial memory. So in this example, so here it cannot see objects, it has only touch. So on the bottom right is his spatial memory, so it places interactions in spatial memory. But here, in addition, it can simulate sequences of interaction that it has previously learned. So those blue symbols here are simulations of sequences. So as time goes on, it learns longer sequences, so it simulates longer sequences. So it provides a second level of choice. So now it is able to simulate the fact of turning twice and go back one step, which allows to generate this behavior of moving towards a flower here, and which is a form of reasoning. And because it has these positive interactions of stepping on a flower, these flowers becomes a goal to reach. Of course, it has to see it. So here it doesn't see the flowers. It has not felt it through touch, so it will never move towards it. But when we introduce another flowers, it can becomes a goal to reach, just because we gave a positive value to stepping on a flower.
C'est très exploratoire. Je le refais. Donc au début, il pioche les interactions au hasard, il ne fait pas de simulation parce qu'il n'a pas.
So let me do it again. So at the beginning, it randomly picks interactions. It has no idea what they mean. And here it has not yet learned sequences, so it has very poor simulations of behavior. So here it managed to simulate the behavior of turning back to the target. And here it knows that the target is in its spatial memory, and by simulating, here it lost it. Okay, here it is placed in spatial memory, and which allows it to find a behavior to reach it again. So we managed to develop smarter behavior thanks to this possibility of simulation in space.
Voilà, c'est tout ce que je voulais vous montrer pour aujourd'hui avant qu'on passe aux travaux dirigés. Mais on va pas, les travaux dirigés, on va pas aller jusqu'à ça.
Okay, that's what I wanted to show you today before we move to the exercises.
Ouais, en fait, ça permet plus de créativité, c'est-à-dire ça permet de tomber, c'est-à-dire le fait qu'il puisse simuler ces séquences dans l'espace fait qu'il arrive à se rendre compte de choses dont il n'arriverait pas à se rendre compte.
The fact that it can simulate sequences in space allows it to find out certain behaviors that it will not be able to find out if it had only the sequential learning. And yes, it's a form of reasoning, but very rudimentary.
D'autres questions? Alors on va reprendre les travaux dirigés, on va faire comme on a l'habitude de faire, donc on va se faire une petite pause avant.
Okay, so the exercise.
L'exercice d'aujourd'hui. Donc on est toujours dans la même logique. On a toujours notre agent.
So we still have an agent that has one bit of choice and one bit of result. So 4 interactions.
On a donc on avait l'environnement 0. Il veut faire 1.
So we have this first environment where it does E1, it receives R1, it does E2, it receives R2, and the second environment in which it does E1, it receives R2, it does E2, it receives R1. and the third environment in which it has to alternate to receive R2. So E1, R2, E2, R2.
Qui est l'environnement 3. Alors l'environnement 3,
So we're going to do the third environment.
l'environnement 0 pendant les 10 premiers cycles.
So this environment will behave like environment 0 during the first 10 cycles, and then like environment 1.
Ça s'adapter une première fois.
So the agent will have to adapt a first time,
Bien sûr, on va vouloir
and then
un agent qui marche à la fois
to
dans
readapt to the other environment.
il avait fait jusqu'à présent. C'est le 1, le 2, le 3. Le 1, le 0.
And of course, we want to implement an agent that is able to work in any of the three environments that we have done before. So here's the implementation of environment 3. So during the first 10 cycles, if I do E1, I get R1. If I do E2, I get R2. And after the 10th cycle, if I do E1, I get R2. If I do E2, I get R1. So to manage to do that, we'll continue what we started last week. So we have this mechanism of activation of composite interaction. So in a context where it does I11, it reactivates I11, I11, which suggests propose I11 again. But when the environment changes, it will learn another composite interaction. Namely, I did I11, but then I did I12. So in the context in which I did I11, I will have two conflicted propositions. So the agent will have to choose amongst those two propositions. So to do that, so here it has two different experiences in the same context. So to help him choose, we will just count the experiences and we will give them a weight. So we count how many times in the context of I11 he did I11 and how many times in the same context he did I12. So we'll add a weight on composite interactions. So what's in green here is what we add from the previous exercise. So when we construct a composite interaction, IT minus 1 IT, we will give it a weight, and if it already exists, we will increase this weight. And if it does not exist already, we create it with a weight of 1. And then, when we make the decision, as before, we create the set of activated interactions that match the interaction that we just did. But we get several activated interactions that may be contradictory. So for each activated interaction, we'll create a proposition for the post-interaction of the activated interaction, its experience. And we will give a value called the proclivity. We'll attach this proclivity value to the proposition, and we compute it as the weight of the composite interaction. So the more we did this regularity, the more we tend to re-enact it, multiplied by the valence of the post-interaction. So if it's positive, we will tend to want to do it again, and if it's negative, we'll tend to avoid it.
Et donc, pour chaque expérience, c'est-à-dire E1 ou E2,
so for each experience that the agent can choose, we will sum all of its propositions.
L'interaction activée qui vont proposer une expérience, on va regarder sa valeur de proposition totale. Et
we look at its total proposition proclivity,
donc je vous ai donné un peu
and we choose the experience that has the highest proclivity. So it becomes a bit more complicated. So here is the code that we are going to implement. So in the class interaction, we are just adding one attribute, the weight, that will record how many times we enacted this composite interaction. So here is the code of the decision mechanism.
On va créer une liste de propositions.
So we create a list of propositions for the different experiments.
Donc cette liste de propositions, on va la créer de cette façon.
So
on va regarder quelles sont les interactions activées. Donc
so we look at the activated interactions.
c'est celles qui sont activées par le contexte courant.
So the composite interactions that match the current context. And for each activated interaction, we create a new proposition.
Donc une proposition, ça va être proposer de faire une expérience.
So the proposition will propose to do an experience. So it will propose to do the experience of the post-interaction of the activated interaction with a proclivity value, which is the weight of the activated interaction multiplied by the valence of what we are going to do, that is the post-interaction.
Et donc, on va regarder si cette proposition elle n'existe pas, on rajoute dans la liste.
If this proposition for this experience does not yet exist, we add it to the list, and if it exists, we only add this proclivity value to the existing proposition. Then we sort the list of proposition, and we take the first in the list, so the one with the highest proclivity value.
J'espère que ça vous inquiète pas trop. Le code est là.
So I hope you are not too worried. The code is here, and of course I will be with you to help.
Donc les traces. Alors là, je vous ai mis les traces qu'on est censé obtenir. Alors, c'est les traces qu'on était censé obtenir dans l'exercice précédent. Donc, motivation 1, environnement 0, c'est les traces.
So to give you an idea of what the traces we seek to obtain, so here are the traces of the previous exercises. So the last exercise is this one. So it does E1, it receives R1 here. So it learns E1, R2, E1, R1. Then E1 again, so it learns E1, R1, E1, R1. So we see that after a while it learns to alternate E1, R2, E2, R2, E1, R2, E2, R2 to get a positive value 1, 1, 1, 1.
Non. Non, parce que faut.
So here the student is asking for the solution of the previous exercise, but I'm not going to give it.
Donc il faut finir. Alors en fait, ça va être ça va être le dernier. Le problème que je vous ai posé aujourd'hui, ça va être le dernier. Hein, on n'ira pas plus loin derrière. Donc on aura cette séance-là pour le faire. Et on aura aussi la séance de mardi prochain pour le faire. Donc il ne faut pas s'inquiéter. On n'ira pas plus loin derrière. Alors on n'arrivera pas à faire un agent qui arrive vraiment à exécuter des Donc, vraiment, ce que je voulais vous montrer simplement, c'est cette idée donc de raisonner sur les interactions composites avec un poids pour pouvoir gérer des situations qui sont pas, disons, un peu probabilistes en fait. Voilà.
Et donc ça, une fois qu'on l'a fait, il faudra le rendre avec notation, etc.
Ouais. Donc ça, il faudra le rendre pour le 15 avril. Donc on a eu 1 heure là pour le faire ensemble et on aura encore 1 heure et demie la semaine prochaine pour le faire ensemble.
Et plus une semaine pour finir encore.
Et plus vous aurez encore même 2 semaines en fait pour finir. Donc ça doit être jouable normalement. En théorie. C'est pas bon là c'est un peu compliqué. Ouais, c'est un peu compliqué vu comme ça, mais je pense qu'on devrait y arriver quand même en réfléchissant de. Vous avez des questions peut-être? Ah oui, je vous ai pas montré la classe proposition. Non, non.
So here is the class proposition. So that will be an additional Java lesson. So the class proposition will implement the comparable class in order to compare them and find the highest proposition. So a proposition will have an attribute experience, what experience it proposes, and a proclivity, which is the strength of the proposition. So when we create a proposition, we will create a proposition for a specific experience with a specific proclivity. We will implement the method compared to that allows us to comparate propositions, and a proposition will be greater than another one if its proclivity value is greater than the proclivity value of the other proposition. We will also implement the equals method. Two propositions will be considered equal if they propose the same experience. So if a new proposition already exists, that is equal to another existing proposition, then we will only add its proclivity value to the existing proposition. And then we choose the proposition with the highest proclivity. So the proclivity, so let me go back to this slide. So you are in the context where you did I11, and in this context you have two contradictory experiences. So first you did I11, then I11 again, and you have the other experience of doing I11 and N12. So those two activated composite interactions propose contradictory experiences. So the proclivity is a mixture between the weight of the activated proposition and the value of the intended interaction. So the highest the probability of success of an interaction and the highest value of the interaction will generate the highest proclivity to try to enact this interaction. So when the agent has to choose between two possibilities of interactions.
Très probable,
Uh,
mais qui a une petite valeur.
it will balance the probability of success with the expected valence
Valeur, ça va passer
in case of success.
on multiplie les deux. Et c'est ce qui fait que du coup il va choisir celle qui est le plus probable et qui a la plus grande valeur. Et donc il va bien réussir.
So this mechanism will allow the agent to succeed in enacting the positive interactions in any of the different environments that we have.
De toute façon, il faut finir déjà l'exercice de mardi. Je pense que tout le monde ne l'avait pas fini. Et je pense qu'en le finissant, ça va clarifier les choses.